right, sorry. Not just you. Not just you. That came across. Yeah, you should be, Connor. That's not what I meant. That's not what I meant.
Joke's on you, I got 94 on my last exam.
Did you really? I mean, of course. I mean, Connor, of course you did. Of course you did. I wouldn't expect anything.
I'm just as surprised as you.
Yeah, that's right.
This is geotexture.
Geotech structures. All right. Okay. That's it. An A's an A. An A's an A. Win's a win, right? No.
I need all the ones.
Yeah. Okay. So you're talking about composite construction. That's putting a deck on top of a pre-stressed member. And things get weird, right? Things get pretty weird because you have stuff that's pre-stressed, and then you have things that aren't pre-stressed, and you have different concrete strengths, and then you have composite action after a certain point. And we're going to try to, solidify some of that. We talked about some of the pros and issues. So this is under the section of like issues, like some issues that might come up. And we went down, the slab is the concrete member is pre-stressed, or the precast member is pre-stressed, but then the slab is not. And then we'll talk about how to deal with that shortly. And then we have the effective width. Okay, that was something I think you probably learned. Those of you who took concrete, even though there's if these T's are spread out. When we talk about composite action, sometimes you can't use the full, like you can't go all the way halfway to the other side. But what do we use for this effective width? And if you remember in ACI, it's the same that you use for regular concrete. It has to do with, it's either the spacing, it's either the spacing in between divided by 2, or it's another value, and you grab the smallest of the 3 or something like that, right? And it's called be effective. That's at play in here too. Right? We're not going to deal with it. We're not going to use it for like the homework and stuff, but there really will be a be effective. Is how much of that slab can you count on, right? As being composite, because at some point due to like shear flow, it's not going to be, it's not going to be engaged, and so it might not be halfway. It might actually stop part of the way, and then there's part of the slab in the middle that just isn't under load, that we don't count it as being part of the composite action. Okay. The other thing that's happening too is there's shear transfer. Right, so if you picture, I just kind of drew 2 different materials, right? So this is, I think yours is hand drawn ugly, but mine, I put it in, I fixed it since and made it like actual arcs. But if you take 2 materials and you bend them, right, there's going to be 2 separate elements, and you try to bend them, there's going to be the shear transfer that happens in between, right? That if you want them to act compositely, you have to provide a way of transferring that shear so that they don't displace like this, right? And that's what we saw on top of that beam is you had rebar that was going up, like this, right? If you put that rebar in, they won't deflect like this, right? They'll deflect together. They'll be one big member as opposed to deflecting separate. And then I always have to put it indirectly. It always ends up with, I always do that, right? Looks like a face. Accidentally, it looks like a face. See the eyes and then the smile? No? No, Kyle? He doesn't. Somebody pointed that out years ago in my notes. I was like, oh, you're right. It does look like a face. Okay? No? You guys not in the mood today?
I see.
Now I see it.
Yeah.
I thought your red circle was supposed to be.
No. There we go. See, there we go.
Nick was asking.
There it is. There's your face.
Yes.
Yeah. Maybe your imagination is hurting. Because you didn't see enough of movies like that. Okay, so how do we handle? Right, so let's like actually dive into how do we calculate stresses and stuff like that in here. Okay, so that, by the way, like if you do bridge design, this is a very common thing. Do you do this?
I haven't done it yet.
Yeah.
But the thing I was just checking. I was just checking effective width.
Yeah. Yeah, that's right. See, I teach real things in here. I teach real things. But see, I'm guessing on what they do in the real world, but I'm a pretty good guesser. Right, but, I mean, it's very common, right? You have girders that are spaced out, and then you don't necessarily, like the bridge we did in Wisdom, it was just a bunch of like double T's that were stacked next to each other, and so then there was no need for a slab on top because the riding surface was just the top flange. But a lot of times you just have separate girders, and you have to tie it all together, and you put a slab on top of it. So how do we calculate that stuff? Okay, so this thing, it's gonna be composite eventually. So it's very, keep that in mind when we're doing this. When you first cast the pre-stressed member, it is just a pre-stressed member, right? And so all you're popping up and then the stuff like that, that's all still the same. And then once you cast the concrete, we'll write all this down, but once you cast the concrete on top of it, right, it's gonna make it deflect a little bit, and it's gonna come down a little bit. But right when you put that load on it, that concrete isn't loaded. The slab you put on top, it's not loaded all because it's still wet, right? And then it hardens in a neutral state. And then at that point, when you push it down, then it's gonna be composite. But before then, it's not composite. So you have to like analyze the beam to start with, and then it becomes composite, and you finish the analysis with a composite. But all those stresses that were in the pre-stressed beam are still there, right? From the pre-stressing and then carrying the slab weight and all that stuff, they're all locked in there. And then after that, it becomes composite. So all the loads after that, that's when you do transform sections. All the loads before that, you don't do transform sections. We got it. I mean, I have all that stuff written down here, but like just a foreshadowing. So this is just after they've become composite. You guys doing this in eGen 415? Who's not in eGen 415? You're all in it. Except for you, Noah. Oh, I totally. Sucks to be you guys. Oh, Connor, you took it last time, though. Yeah. So it actually works out perfect timing because she's talking about it right now.
And you
see who does it better. Let's just see who does it. Who does it.
I thought you said you do it the same way.
We do, but just the presentation, right? The presentation of it. Let's see. Or the explanation of it. She's probably going to be her. It's probably going to be her. She's more organized. Okay, so what we have to set this thing up, we have two different materials, right? So this is just a rectangle to start with. We've got the rectangle made of material 2 down at the bottom. We've got another rectangle on top, so this would be like my pre-stressed beam, ignoring the pre-stressing, and then I have the concrete slab on top of it, okay? The cast-in-place concrete slab on top of it. Over here is the stress-strain response of those two materials, right? The concrete for the pre-stressed member is gonna be a lot stronger, right? Because it is, it's like what did they say? 13 KSI is what they were using for their the Missoula concrete. So it's gonna be very high strength concrete, which means it's gonna be very stiff concrete because of the 57,000 square root F prime C. Okay. Then this blue one right here is the slab concrete that's on top, the cast in place slab concrete on top. And it's like a 4 KSI. So its modulus elasticity is gonna be a lot less, right? It's gonna be more flexible. Okay. So the blue corresponds to the blue, the black corresponds to the black over here. So then all of these things have the same linear strains. Plane sections remain plane, okay? Plane sections remain plane, so these are what those strains are gonna look like, okay? And then what we're gonna do is come up with what those stresses are. And what you do is you come in and we assume that there's a linear strain distribution across the cross section like this, right? All the stuff down here is material 2. Okay, and so what you would do is you come over and you look at your strain, and you come over here, and it would, well, it gets a little more complicated than that. We would have to assume that this is going negative 2. This is going this way too. But concrete doesn't do that, so it gets really weird because, right, concrete, you wouldn't get these stresses right here because it would crack, right? And so, like, assuming that this thing can carry tension, just for the sake of doing this composite section stuff. So I would go over here, I would get the strain here, I would look at the negative strain, and I would get a stress, and I would write that stress right there. Then I'd go up here and I'd get a strain, I'd come over here, see where that strain is, that would give me a stress, I would write the stress right here, right? So you go strains to over here to then stresses like that, okay? Then we get up to the neutral axis, obviously there's gonna be 0 strains there, which means there's 0 stresses, you'd be at this point right here, and you keep going up until you hit this point right here, okay? So that point right there, we would call, what do I call that? I call that strain. On my notes here. What do I call that? I call that strain B. So I'll write that right here, strain B. Strain B. Okay? So I go over to strain B, and I draw it on here. Right? Because we're trying to look this stuff up at a certain strain. So that'll be right. We'll make it, I'm going to do it dashed. Okay, this is strain B. No. Strain B. Okay, so depending on what material I'm on, right, that strain B is going to give me one of two stresses, right? It's either going to give me, it'll give me this guy if I'm on material 1, and it'll give me this guy if I'm on material 2. Okay, and we'll call this one right here, we'll call this sigma 1, and we'll call, oh no, sigma, what did I call it over there? Sigma B. Okay, and this one up here we'll call sigma C. Okay, if I am on, so I got strain B right there. If I'm on material 2, which I'm working my way top to bottom, or bottom to top. If I'm on material 2, it's going to get returned to me sigma C. So this would be sigma C right here. Right? If I switch, right, I'm right on the border between these two things, right? If I'm right on the border between these things, so if I immediately switch to 1, it's going to give me sigma B, which would be this point right here. Sigma B. Right? It has less stress there, right? And then I keep going up. This would be, what do I call it over here? I call this epsilon C. Epsilon C right there. Epsilon C would be over here somewhere. Right? And that's going to give me what I called sig. Oh my God. I got two. This is why Carissa's going to do better. She's going to use better variables. We'll call that one sigma A. And this right here would be sigma A up at the top. Right? The whole point of this, right, of me doing this, is that there's going to be a kink in the stresses, right? There's a kink right here, right where it switches materials, right? And because this material is more flexible, then it's going to end up with less stress right there. And then since this material is more stiff, it's going to have more force right there, okay? And so the whole point of this, like, this is great, right? Like, you could do it this way. You could analyze it this way for sure. You could just go through and work my way around. And then based off of these, now I could determine what the forces are that are coming from those stresses. And I could figure out what the forces are coming from these stresses and which direction they're acting. And I could sum them up, and that would give me a moment. And I could calculate my moment based off of those. That's the way Carissa used to teach it, was doing it that way, where it's like all based off of, sigma A, sigma B, sigma C, and then you look at, like, that's a trapezoid, and then you can figure out the section of the trapezoid, and that gives you a force and stuff like that. The other way that you learned in mechanics of materials, so this is really just a review of mechanics of materials, the other way you could do this is doing MY over I. MY over I is beautiful, right? We've used that in all sorts of things. If I want to use MY over I can do it, but you just have to trick this thing a little bit, okay? And how you trick it is what you end up doing is you pretend that this is a different width. And if you pretend that it's a different width, then you can make it so that, in this case, we pretend that it's narrower, which means the stresses would go up, which means this then just becomes that. You get rid of the kink. You get rid of the kink. You get rid of the kink by pretending that element is shorter or is narrower, but making it narrower, it shifts this over to the right, so then it lines up, and when it lines up, you can use MY over I. That's the whole thing that we're doing, right? We're just shifting it over. So this is what it is. Oh, it actually says right here. We pretend that the flange is narrower, so stresses go up to match those in the pre-stressed beam. This keeps the same resulting forces acting at the same locations, and that allows you to use MY over I. So what it turns this into, right, just to kind of draw it down, is it does this. Right? It shifts it to the right. And so then now you can use MY over I. Does that make sense, right? Like you pretend this is narrower, which will then increase the magnitude of the stresses, right? It'll drive them up. And so you pretend it's narrow, so it drives them up, and then when you drive them up, this line right here just shifts to the right, and then you can do that. And so once it lines up, my over I, right? And the way you can do that, how much you pretend that it's narrower, is based off of this n. What's the n stand for? Did she tell you that?
Ratio of moduli.
Yeah, it's right. But does it have a name? It's like
Nondescript.
the moduli ratio. Call that. I don't remember either. It was an n. So you do a ratio between the elastic moduli, moduluses.
She did the
Moduli.
same. She did the
Did she really? Yeah. Smart woman. So you do, in this case, it'll be the one you're trying to transform over the other one. So it'd be EC1 over EC2, right? In this case, what we're going to end up doing is going to be EC slab over the EC of the pre-stressing. What up, Neil?
So, scale factor.
Scale factor? Oh, it's called scale factor, is what she said?
That's
Okay.
in her notes.
Yeah. And so that's what it is. So then the B transformed, BT, is just N times B, okay? And so then then this value will be less than 1, right? It's EC is smaller than EC2, so it'll be less than 1. And so when you do N times the actual width, B's the width, it'll make it narrower. And so then it'll drive those stresses up. Then you can use MY over I, okay? But then you gotta be careful, right? Well, because a couple things, because the pre-stressed beam is already stressed, right? What you have to be careful of when you do this is that once you calculate stresses, you have to then transform them back when you're back up here at the top, because it'll give you what it's going to return to you. My over I is going to give you the ones out here, but then what you really want is you then have to multiply it by n to get them back to what they actually are. Okay. Yep. So we'll lay that out. Okay. So what we do, this procedure, when you do a transform section analysis.
Pre-stressing, does it matter if you make the weak material narrower or the strong material thicker?
I think you could do it either way. It's just a little bit easier doing it. That's just the way we've always done it. But you could. If you want to complicate things, do it the other way. She does. Oh, yeah. It doesn't matter. It really doesn't matter. You could go either direction. It's just a little bit easier here because we'll get when you do the transform sections, like a lot of times you know what I is. Like maybe it's like a bulb T or something like that. And the I is pretty complicated. And so you could use the parallel axis theorem to do it, and then it's easier to do it that way, where you leave the pre-stressed member alone, and then you just modify the rectangle, right? I'll show you in a second. All right. I don't know what's going on with this guy today. Right. So what you do when you do this, you start out by transform the section. Right? Keep in mind, you don't do this from the get-go. The pre-stressed member is the pre-stressed member, and then that kind of gets locked in. And then once the concrete, it's all the loads that are applied after the concrete is cured on top, the slab is cured on top. Then you have to do this stuff. But just in general, right? You transform the section, right? In this case, it's going to be BT is equal to N times BE. In this case, I think your homework problem, I'm just going to give you the width on top. But really, technically, you would do what we were talking about earlier, coming up with the effective width. Okay. Then once you transform that section, you then have to come up with transform section properties. Right. You calculate the section properties given this now modified thickness, right, or width, modified width. Right, in this case is with narrower flange. Right, things we need, right, are I. The other thing that's going to move is your neutral axis moves too. Right, your neutral or your centroid changes when you do the transform sections. Centroid, and so therefore your C's are going to change, right? Your Y's, your MY over I, those change. What Y's you use because the thing moved around. Okay. The CGC moves. Okay, but again, it's complicated because the beam is kind of separate. Then you calculate stresses in beam and slab using transformed section properties. Okay, using my over I. Right. And then the last step is you transform the stresses back. To real stresses using N. Okay. So again, these are just the procedures after it's cured and it's acting compositely and you apply the load as deflecting. Before then, though, right, it's on its own. Okay. Give me a second to write that down, Gavin. Slow.
Thank you.
Yeah. Do you type it?
Yeah.
You do. Good. Good for you. Anybody else
Well, I
type
can-
in or is it just me? Just me? Me and Gavin?
I can read my work. if I
Yeah,
type it.
that's right. Me too. Me too. We good? Okay.
All right.
Oh, no, you're not. Okay.
All right, we're good.
Okay. Load stages. Okay, just again, just we're gonna be setting the stage here. The first load stage, right, is initial loading. Right? This is all pre-stressing, right? The slab isn't even involved. Pre-stressed beam properties. Right? That's all we have to deal with there. You're going to be using FPI, right? Because just like regular stuff, right? The pre-stressing force before the losses. F prime CI. F prime CI. Right? We're using that material property before it's gain strength. Assuming simply supported, which I think is all we're going to do in this class. It's going to be compression, bottom, tension, top. Right? That's what we're worried about, right? The popping up, compression, bottom, tension up at the top. That's going to be the load, the case that controls, right? And then what we use for the load on this is just going to be the self weight of beam, right? Of the pre-stressed member. So everything's the same so far. Okay. Then we do slab placement right afterwards. All right. So now the beam, take it out to the job site, put it in place, lay it all out, put the formwork for the slab, put the slab on top of it, and then right as soon as you put the slab on top of it, what kind of loads are we going to see and what we have to check? Okay. It's going to be a lot of load on there, right? So it's going to be, again, at this point, it's just going to be the pre-stressed member, right? The concrete can't carry anything yet. It's still wet, right? Pre-stressed beam properties. Just that again. This time, though, right, even it's like, it can be quite a while later from when it gets cast and then brought to site and put in place. And so in that case, there is going to be some pre-stress losses. And so we're going to use the effective pre-stressing force. It's going to be lower than what it actually is, right? Because the actual pre-stress force is at 5 years, but we're going to use the 5-year mark here, the FPE, just like we did before, okay? At this point, our concrete's going to be F prime C, our 28-day strength. Let's go down here, F prime C, not I. See, fine motherfucker, dude. Starts filling in for me. Right. This is for the pre-stress member. Just to keep it, right? It's just the pre-stress member strength at this point. Okay. And it is the 28-day strength, just like we've done before. 28-day strength. That's what we use there. And what we're concerned about in this case is tension bottom and compression top. The load we use in this case is going to be self-weight of beam and slab weight. So it has to carry both of those, right? Because at this point, right, you imagine just the pre-stressed beams going across, all the formwork sitting there, and then you cast the concrete on top of it with all the formwork and whatnot, and it's all wet, and so it's just going to have to be carrying all that dead load, and which is significant, right? Because it's the whole deck, it's the whole top of this thing, so it's going to be a significant amount of weight that it has to carry. Okay. To get really crazy with it, James, he talked about post-tensioning afterwards. They can post-tension at this stage, which is weird. So you could have, in your pre-stressed member, there could be ducts. Could be ducts. But typically ducts along the length, right? Or they could have those post-tension tendons stretch or included throughout. So then you cast the concrete, and then you let that concrete that you just placed come to strength, and then it's composite, and then you can post-tension it and then pop it back up. And you can see why you'd maybe want to do that, right? Because you can only pre-stress it so much because it's going to pop up on you, right? And so you can only pre-stress it so much, and then you come and put this slab on it, and it takes away a lot of what you just put all this pre-stressing in to carry stuff, and you put this slab on it, and it just cancels a lot of that stuff out, right? And so at that point, it may be even sagging down a little bit. You imagine you can just post-tension it afterwards where you can get it to pop back up so that when you put the superimposed dead load on and the live load on, now it's, now you've got a positive camber again, and then you can push that down again with a load. So they do this. We're not going to do it. We'd lose our minds if we start doing it. Because if you think about what happens, right? So now you have this pre-stressed member. I'll write this stuff down. You have pre-stressed member, slab on top. Then you come in, you let it settle down a little bit, then you post-tension it. Well, what's that post-tensioning going to do? Well, it's going to cause it to pop back up, but it's going to be composite action at this point because now the slab has come to strength, and then now it's acting compositely with your pre-stressed member. So now it's composite. So we just learned how to do it. You have to transform sections. But then also that post-tensioning, what's it going to do to this? My pre-stressing force in my beam. It's going to make it go down because I'm going to put post-tensioning on, and I'm going to squish it more, right? So I'm going to even remove all the other stuff. If I just have a pre-stressed member and then I just stretch the steel, concrete, slice it, squishes, now I'm coming back and I'm putting post-tensioning on, and I'm squishing it even more. And so then you're going to get elastic shortening of your pre-stressing member or your pre-stressing steel, and you're going to lose. That FPE is going to go down. You're going to get losses on that. So then it's going to go down even more. But then you've added in post-tensioning, so it kind of can't. It gets good. We're not going to do it. Stanton's notes go through that whole, everything you check. We're not going to do that because it's too hard. I look out at you and I'm like, we can't handle this. No. I don't want to do it either. I just oh my God. I think there's so much bookkeeping. It's just bookkeeping. So much bookkeeping involved. I think that they use the computer program for doing that, right? But know what the computer program's doing. Okay.
When you put that slab on, are you always going to have tension at the bottom and compression at the top, or is that dependent on?
Depends on how much pre-stressing you have. But just because you're right, because you could have put so much pop up that you put the slab on top, and then it's not. It could still remain tension on top, compression on the bottom because the slab isn't there,
So
right?
it depends on.
But then what will control the design? That'll be the worst case scenario would be no load on it. The initial tension top and compression at the bottom. And so really that load on top is just going to help you. It's going to be less. And then the thing that you should be concerned about is if it flips and then starts bending down. And so that's why I say there. But technically you would still have to worry about tension top, compression bottom, but that won't be as bad as the case before, which was, that makes sense. Because then also your pre-stressing force went down and you have the load canceling it out. And so, but you're right, it could, because depending on how much pre-stressing you put in there, it could still be popped up. Right. Okay. So what are we going to write here? There's lots of shit to write down. Right. You can. Oh, you motherfucker. Oh. I should listen to Ernie. Don't do it. Post-tension after slab placement. Really complicates things. Right, what happens, just some highlights there. In this case, you would flip around. It'd be compression bottom, tension top. You go back to that case if it popped up. That's what you put in that preset. It would pop back up and you would be compression bottom and tension at top. And that'd be the controlling case there. What else? Oh, composite properties, calculating effects of right. And this is the transform sections, because it's now actively it's composite now. That concrete can carry load. And you'll do FPE for pre-stressed member, but need to adjust for loss due to elastic shortening. See, this it bogs down. If you go too long on this text box, it bogs down. Elastic shortening due to post tension. But then what's interesting though, for the post tensioning, you just did it, so you're actually using FPI for post tensioning. Oh, why did that change size now? Oh, you son of a bitch. Now it's back. FPI for post tensioned steel. Right? Because it's brand new, right? We just put it in there. Right? And then what we use here is self-weight of beam and slab. That's slab. Not saw, self-weight. Self-weight of beam and slab. This is before we put anything on there, okay? And then we're gonna skip over that one, right? We're not gonna do post-tensioning, and so we'll go right to this D here when we do it. Total service loads. And under here, now things are acting compositely, so we're gonna go put composite properties. Properties. Right? That's what I mean there. Again, is transform section. We'll have self-weight of beam and slab and dead load and live load. We use FPE. And effective pre-stressing force for that. Okay, but even this is a little misleading. This is a little misleading because the self-weight of the beam and the slab, right? That's not going to affect the composite member because those are already the beam is already carrying. The pre-stressed member is already carrying the self-weight of the beam and the slab. What the part that the composite section has to carry is the dead load and the live load. It's the stuff that's added afterwards. That's what it has to carry. These are already locked away. The self-weight of the beam and the slab are locked away in the pre-stressed member. Compositely, though, the composite section will just carry the dead load and the live load. Okay. And then, again, just note that the CGC moves. We mentioned that before. Right? And so it gets a little confusing. This came right out of Stan. So he tried to like formalize this. He's just like, oh, I'm going to turn this into, these are what the things that you have to check along the way. And then and I just used to put it up there and say, here, go with it. And then over the years, the students have found many, many mistakes in it. Like he just uses wrong. I mean, look at all these subscripts, right? Right? He uses all these different subscripts and he messes up throughout. And we're like, oh God. And so, and this also works for the post-tensioning as well. The post-tensioning. So it's got some cases in here that we're not even going to look at. And then some of the stuff too is repeated. So I, in my infinite wisdom, made my own. Okay, and then my first version had many errors in it. Okay, and so the students were able to piece through. I was looking, and I think that the students were able to identify all of my errors, and so this should be okay. Okay, and I'll talk about that. Let's see. Hold on. No. Let's see what we have left here. I do the horizontal shear. This ends, this here, post ending. Okay. Yep. Okay. All right, let's do this. All right. So let's look at here. These two right here up at the top. These two right here. These are the initial. Right. Right, so this is just the casting of the beam. Right. No slab at this point. Just cast. Okay. And what and this should be, this is just review. We've done this before. So this is going to be compression bottom, right? So under normal conditions, right? Under just simple supported, that's compression bottom, and this is going to be tension at the top. Okay, and we'll just look to see what those are, right? Compression bottom, tension top. So this is the popping up, right? So this is just the same value. This is the same equation we used before. So this is going to be, you're going to use the FPI, so the initial pre-stressing force. This is the area of concrete of the precast member, because this is done with precasting, by the way. So the PC here stands for precast. I guess we should probably label some of these things. Let me try to label some of my nomenclature throughout. PC equals precast. Right, there's some other ones. Self-weight, that's self-explanatory. FPI is self-explanatory. We've used that before. Precast, self-weight, precast. CIP is cast in place. Capitalizing that. CIP equals cast in place. So that's going to be this slab concrete. Comp is composite. All right, that's the composite member. That's all of them that are new to us. Okay. Okay, I think that's enough now. Okay. All right, and so then we come down. This one, same thing, right? We used this one before. Use an effective pre-stressing. This is the area of, or I guess I never finished this one. This is the area of the concrete just for the precast member. Okay, and then this is S1 of just the precast member, and this is S1 of just the precast member, and we're just doing the self-weight of the precast member. That's it. No slabs or anything. And so that's the initial case. This you're checking to see, is it going to pop up too much? You're going to get tension at the top or compression at the bottom. Then we come down. This would be slab placement. Okay, it would be slab placement. Right. Slab placement, we just had this discussion, right? It's going to be potentially, you're going to run into problems at compression at the top and then tension down at the bottom. That's what each one of these things are checking. Right? In this case, we're using the effective pre-stressing force. And again, all we're doing is just the concrete, the area of the concrete of the precast member. The only thing that's carrying all this is just the precast member. So these section properties, that's the precast member, just the precast member, just the precast member. But then now notice that we've added on to it the self-weight of the precast member plus the self-weight of the cast in place, right? So the slab concrete on there as well. And so it's always kind of weird to think about like that concrete not being loaded at all, right? Your cast in place concrete, when it's cured, even though it's like spanning a big difference, it's at a zero stress state right when it first starts. It's kind of weird because you cast it in place. I mean, it had to span that whole distance, but it's not spanning it. The beams underneath it are spanning it. And so that concrete on top is just in an unstressed state at this point, right? Because it's wet. And then it hardens in a wet, from the wet state in an unloaded state, and it's unloaded. So this is just basically the same case above, except for it's reversed. You're worried about compression at the bottom, or compression at the top and tension at the bottom, potentially, right? Potentially, if it's not, but this slab is usually pretty heavy, so it should be this case, okay? And then you're just using the section properties of the precast member, and then you're just adding on to it that weight there, okay? So now we're down to here. Now this is, what do we do for the total load? I'm skipping over the post-tensioning, right? I'm going straight to this guy. Right? In this case right here would be slab, I think it's total load. After slab cures and superimposed loads or load added on. Superimposed loads. Okay. There's a lot going on in here because you have the slab. You have to check things in the pre-stressed member, and you have to check things in the slab. That's why there's 3 cases here. Okay. The first case is going to be, and we'll write this down next time, but this first case is going to be compression at the top of the pre-stressed member, right? This is compression at the top of the slab, and this is tension at the bottom, right, of the composite member. And so you have to check all of those things. Okay, there's 3 things because you have to see what is the slab going to be okay? Is the pre-stressed member going to be okay? You can see this N that's in there. So we'll finish talking about this next time. The next thing we're going to do is talk about checking ultimate capacity, then shear capacity. Just got a couple little notes on there. How they design for horizontal shear, that shear transfer. A little bit about deflections. Cover some loose ends, just to show you that some of our assumptions throughout were okay. And then that's it. That's it for the pre-stress stuff. And then we're gonna do post-tension next week, and then start running. And then after the post-tension, I think it'll take about 2 weeks. It'll be 1 assignment. Kyle's gonna come up with some sort of assignment in between there, and then we'll do an exam after that. And it's kind of like a final, but it's not, because we're also gonna do a little bit of bridges, and then we'll be a test of bridges afterwards. So. And then the bridges one ends up being a pretty easy exam, and a lot of you need that easy exam to recover from the first exam. So just to set the stage.